Good morning, students. Mr. Carver here. Today we're going to start Chapter 8, 8.1, Concerns Sequences. As the name implies, it is a sequence of numbers separated by commas. And in Section 8.1, we're going to explore the behavior of these sequences as you go from the beginning of the sequence out to an infinite number of numbers in those sequences. They are sometimes written in this form. They are other times written in the nth term sequence form, such as something that might look a little like that. Now, sequences are defined as functions for which the domain is the set of positive integers. Now, by positive integers, we mean we're starting with 1. So a sub 1 in this case will be 2 to the first over 1 squared. A sub 2 will be 2 to the second power, all over 2 squared. A sub 3 will be 2 to the third, all over 3 squared, and so forth. The process that we're going to use to determine the limits of these sequences will be exactly the same as the process that we used in Section 7.7 when we were looking at functions. So the only difference between 8.1 and 7.7 is that in Section 8.1 we're looking at discrete functions that is a collection of individual points for which the domain again is the set of positive integers, whereas in Section 7.7 we're dealing more with continuous functions. So for example, in Section 7.7 we had f of x is equal to 1 over x, and you've got a continuous function that looks something like this. In Section 8.1, we've got a sub n is equal to 1 over n. Now instead of the continuous function, what we get are a set of outputs based on the inputs of individual integer domains. You'll be asked to find limits in this section, so if I might take the limit as, let's get rid of that, and goes to infinity of, say, for instance, 1 plus 1 over n, that quantity to the nth power. The same indeterminate forms from Section 7 apply to Section 8.1. And if you recall, these are the indeterminate forms. You've got 0 times infinity. You've got infinity minus infinity. Let's get rid of that. Kind of out of place there. You've got infinity to the 0, and you've got 0 to the 0, and then, of course, 1 to the infinity. You'll be using L'Hopital's rule in Section 8.1, just like you did in Section 7.7. And so if I take a look at this example here, 1 plus 1 over n all to the n, what you get as n grows infinitely large, this is essentially 1, and this, of course, is driven to infinity. 1 to infinity, of course, is an indeterminate form listed in Section 7.7. So again, the techniques in 8.1 will be exactly the same. What we're going to do in this case is set this equal to y, and then we need some way to get this into a L'Hopitizable form, which means this right here needs to go down to the front. The only way to do that is to first natural log both sides of this equation. And now this n is going to go down to the front using properties of logs. And I'm going to get rid of that. And let's see if I can get rid of that without erasing the entire thing. And of course we check then indeterminate form. Again, as n is driven to infinity, this is in fact infinity, and this is then the natural log of 1, which is 0, and that appears right here on our indeterminate list. So to put it now into a L'Hopitizable form, I'm going to put this into fraction form. And what I'm going to do is take this n right here. That's not the way to do that. I'm going to take this n right here, and I'm going to move it to the denominator, which is going to give me then on the left-hand side the natural log of y. On the right-hand side, I get the natural log of 1 plus 1 over n, and this becomes 1 over n in the denominator. I check which form I get again, which form I am currently in, rather. As n goes to infinity, the numerator here turns out to be the natural log then of 1, which is 0. And as n goes to infinity in the denominator, that is 1 divided by a huge number, 0 over 0. is indeterminate form in L'Hopital's rule, so I can now apply L'Hopital's rule, which simply says I want to derive the top and the bottom. Now this is still set equal to the natural log of y, but when I derive the top, I get 1 over what I am logging times the derivative of what I'm logging, which of course is 0, plus, that's negative n to the negative 2, otherwise known as negative 1 over n squared. Deriving the bottom gives me exactly the same thing. The nice part about this is, since I'm multiplying, I can cancel these factors right there. Now driving n to infinity, of course, is going to give me 1 plus 1, excuse me, 1 rather, over 1 plus 1 over infinity, which gives me 1 over 1 plus 0. So that side is 1. Don't forget, though, that the left-hand side is the natural log of y, which is base e. So y, or my limit, is going to be e to the first. And so what you would say is that this sequence, a sub n, this sequence right there, converges to e, which is 2.718. And what that means is the sequence a sub n is equal to 1 plus 1 over n to the n. As you go out farther and farther and farther into the sequence, you get closer and closer to the numeric value of e. Just like in section 7.7, you've got to be careful to make sure that if you're using L'Hopital's rule, that it must be in indeterminate form. For instance, if I take a look at this one, the sine of 5n all over n, and I take the limit as n goes to infinity, the sine of 5n over n, what I'm going to get essentially on the top is just an oscillating function that jumps back and forth between plus and minus 1, which is, of course, is the amplitude of that trig function right there, while the denominator continues. That's not plus and minus 1, that's plus minus infinity. Now we're cooking, plus minus 1 over the denominator, and the denominator in this case does go to huge. So plus minus 1, or finite numbers over huge, drives those numbers in that sequence to 0. And what that means is you go out infinitely far on this sequence right here, the numbers get closer and closer and closer to 0, and they are said to converge to that numeric value. L'Hopital's rule is a great way to compare growth rates of individual functions for which you might not be familiar with. But if I take the limit of this function right here, or this sequence rather, as n goes to infinity, of n squared all over 3 to the n plus 2, you'll notice that the top grows without bound, and so does the bottom, which makes this a L'Hopitizable function. So if I use L'Hopital's rule here, the top then goes to 2n over the derivative of 3 to the n, and if you recall, that's the natural log of the base to the power times 1, which is still infinity over infinity. So what I want to do is use L'Hopital's rule again. That'll give me 2 then on the top over the derivative of the denominator. Now, natural log of 3 is just a constant, so it stays there. And now if I derive this portion right here, I get another natural log of 3 to the n times 1. And as you can see now, it's no longer in indeterminate form. What I get is 2 over an ever-increasing function in the denominator, which means the bottom outgrows the top. 3 to the n grows much more quickly than n squared, driving the entire thing to 0, so that sequence converges to that numeric value. All right, let's take a look at a couple of different types or special types of sequences. Let's do some factorial. If I've got n factorial all over n plus 2 factorial, remember factorial functions like 5 factorial are defined as 5 times 4 times 3 times 2 times 1. And so we can apply this pattern here to this sequence. If I take the limit as n goes to infinity, what I want to do is just start writing out just some portions of this product in the numerator and denominator. For instance, n factorial turns out to be n times n minus 1 times n minus 2, etc. The top is then starts at n minus 2. That'll be times n plus 1. Excuse me, that's n plus 2, n plus 1, times n minus 1, n minus 2. And we're assuming that this pattern continues as long as that factorial is defined. That is, it doesn't go below 1 on the lowest factor. And then what you'll notice here is that these factors do in fact start to cancel. For instance, my n's cancel, n minus 1's cancel, n minus 2's cancel. The assumption is that the remainder of those also cancel. And so this is essentially 1 over n plus 2 times n plus 1. And if I take the limit then, as n goes to infinity, it is bottom heavy. And again, this sequence converges to that numeric value. It converges to 0. All right, the last special sequence that we deal with here is a geometric sequence. So for instance, if I have something like, let's do 3, 1, a third, a ninth, etc. If you recall, the nth term for a geometric sequence is a sub 1 times my ratio to the n minus 1 power. And what makes a geometric sequence geometric is the common ratio. So what we're doing is every single time we're multiplying by 1/3. That is what defines a geometric sequence. So this sequence right here can be written as a sub n is equal to the first number in the sequence times the ratio to the n minus 1 power. And a geometric sequence will always converge to 0 if the absolute value of r is less than 1. So it doesn't even matter if it alternates. Like for instance, if I have 5, negative 5/3, positive 5/9, negative 5/27. In this case, I would write it as a sub n is equal to 5 times negative 1/3 to the n minus 1. This will still converge to 0 because the absolute value of my ratio there is less than 1, just as it is up here. So both of these sequences will converge to 0. Just a word of caution algebraically, if you have a sub n is equal to, let's do 3 to the n over 5 to the n plus 1, it's helpful if you rewrite it so that you can clearly see what the ratio is. And I think you would agree that the top is 3 to the n. The bottom can be rewritten as 5 times 5 to the n, this being my ratio here. So my a sub n, written more clearly, would be 1/5 times 3/5 to the nth power. This would also converge to 0 because my ratio here is 3/5. All right, the last term that we need to talk about are monotonic, also known as 1-to-1 sequences. And that is, if you recall from chapter, I believe it was chapter 3, we talked about monotonic or 1-to-1 functions. That is, functions that were always increasing or always decreasing functions. That is, functions that pass the vertical or the horizontal line test, not or, and. So the horizontal and vertical line test. So always increasing, always decreasing. But in section 8, you're going to be dealing with sequences. So instead of continuous functions, we've got a series of dots, yet we are still looking for hilltops and valleys. Now, if there are no hilltops and valleys, that means that the sequence is, in fact, monotonic. So if I have a sub n is equal to 3n all over n plus 2, what I'm looking for, again, are hilltops and valleys. And the way that you find that is to find critical numbers of this function right here. And to find critical numbers, what we're going to do, of course, is we're going to derive it. So I've got a prime of n is equal to, we're going to use the quotient rule. It's going to be n plus 2 times 3 minus high, that's 3n times 1, all over the square of what's below. Now, I'm not using L'Hopital's rule. I'm actually deriving a sub n. And so now if I clean this up, in the top I get 6, in the bottom I get n plus 2 to the second power. That is a prime of n. And what you'll notice here is I've got critical numbers at x is equal to negative 2. Now, critical numbers come from the numerator and denominator of the first derivative. No critical numbers coming from the 6 here, but I definitely have negative 2 coming from the denominator. But I can throw this out because critical numbers have to be positive in terms of sequences. What would happen, though, if you did have a critical number that fell in the domain of the sequence is you would put that on a number line and you would test on either side into the derivative. So if I have an increasing set of numbers to the left of 3 and a decreasing to the right, that would not be a monotonic function because I have, in fact, a hilltop. I have increasing to the left and decreasing to the right. Now recall, you're putting it into A prime, which is the slope machine of the sequence. All right. So I think that should probably get you through 8.1. I'll be answering questions. Thanks so much for tuning in. Take care.